So with that, I'm going to keep moving, keep us on track here. I'm going to introduce Aaron Nardi. This topic was actually requested, and so this is the fatigue resistance of cold spray coatings and deposits. And with that, Aaron.
All right, can you hear me and see the slides okay? All right, perfect. All right, so yeah, this talk is going to be a little different than what I would normally present about like materials and processes and stuff like that. It is an area of a lot of interest for me, and we have a lot of folks working in this area with us in academia.
David Lorman.
Across multiple organizations. So I'll mention WPI, for instance. We actually have a paper going out soon with Chris Sample and Diana Rados on crack propagation in cold spray deposits. So anyway, let me get into some basics here. I know most of you probably already know a lot of this, so I'm going to skip through this quickly. Fatigue can really be broken up into, like a few different categories, if you want to think of it this way: initiation, growth, and rupture. We spend a lot of our time thinking about the first two, and that's what I'm going to be talking about mostly today. Obviously, rupture is, it's important to know the material properties from a rupture standpoint so that you know how big your crack can be before you actually have a problem. Fatigue is a catastrophic event in many, many cases, and that's because the part doesn't really tell you a lot before it finally fails. It can if you're inspecting and stuff like that, and there are other instances where you have, kind of leak before burst sort of scenarios in pressure vessels, but by and far, if you've got a high cycle fatigue problem, for instance, the cycles can rack up very quickly, and a failure can occur without notice. So,
and you may move your headset just a little bit back from your microphone. It's a little bit choppy.
Oh, okay. So, should I talk quieter or no? No.
Yeah, or just move the microphone a little bit further away from your mouth. That might do it.
Okay. All right. So crack initiation in the classical sense is dislocations moving, surface roughness being generated, and notches forming and all that kind of stuff. Can also be driven by defects, and that's the more likely scenario in cold spray is defects between particles, especially if that's near the surface, can propagate and form, can link up and form cracks. Residual stresses, surface damage, bedding, corrosion, all that plays a role too. Crack growth, this is a very interesting one, especially for coated structures. Normally we think of crack growth in the sense of, there's crack tip plasticity. We have to grow through that kind of plastic zone. You got closure effects. You got all kinds of stuff going on. But the added caveat in a cold spray or just a general coated structure is we have to also get across an interface. And how a crack propagates across an interface is a very interesting process, and I'll talk a little bit more about that. And then, of course, final rupture. I'm not going to really talk about that piece in this talk. So, a coated structure, oftentimes we're talking about a relatively thin coating on a relatively thick part. Now, that can vary, and you heard from the MAI talk, you could be talking about 1/3 of your thickness or half of your thickness. There's lots of things that we can talk about here, and you have to understand where you are on your real part. So here's an example of a part that's been done. It's been shown before at these meetings. It's the Apache mass support. And there's a relatively thin coating on a relatively large part. So then, once you know what your proportions are, you can then design a appropriate specimen that either mimics it or, maybe it has close to the same proportions, or at least you can separate out and you can understand the load share of your two components of your part. And so when I say load share, an easy way to think about this is like a two-bar mechanism where both bars are being strained at the same rate. Well, the two bars may have obviously different areas, cross-sectional areas, and potentially significantly different modulus of elasticity. And that affects the amount of load share that each one of those components carries. Now you have a bond joint to deal with too. I'm not really talking about that here. That really comes into that propagation question. So now let's look at the two types of curves that I'm going to be showing to kind of explain what's going on here. One is your traditional SN curve. Generally speaking, I'd say we spend more time in high cycle fatigue, which is this portion of the curve. High cycle fatigue is dominated by elastic strains, not as much plastic straining going on out here. We generally test it under a load cycling condition as opposed to a strain cycling that we often do at low cycle fatigue, because with the plasticity that occurs down here, you can actually get ratcheting effects during your tests and stuff like that. So, that's basically what we're looking at. So these are life cycles down here. And then a lot of times we call, where this plateaus the endurance limit. Some materials theoretically don't even have one. But, generally speaking, we say, well, that's the endurance limit down there. If you stay below that stress, you won't get a failure. So now we can look at something like a constant life plot. And in this case, a lot of people call them a Goodman plot, but it's it's a Goodman fit line on a constant life plot, where basically we plot our R equal -1, so fully reversed loading on the y-axis here, and then we plot a UTS on the x-axis. So this is only mean stress, right? So you fail here. And then, you can draw a line in between, and that approximates your design space below it. So what I've shown here is 70-75, rough numbers for 70-75 and for 60-61. And then here you can look at different R ratios, so different stress ratios, different amounts of mean and alternating stresses. And I'm just going to throw on here this kind of parabolic shape. There's such thing as this Gerber parabola, and it kind of describes closer to a real material. The Goodman line is supposed to be a fairly conservative approach. So if we start throwing a bunch of different materials onto a plot where we're plotting ultimate strength and endurance limit, you see an interesting thing. And the endurance limit, this is at R equal -1, so this is on the y-axis of that Goodman diagram. Most materials, and I have a wide variety of materials here, from steels to titaniums, 300M steel. I even have some carbides on here, and then a whole bunch of aluminums down in the corner. They all kind of fall between these two lines. And so, the two numbers are about 0.25 for this and about 0.5 for this. So higher toughness materials kind of tend to fall along this line, and lower toughness along this line. If you blow up the aluminum, because that's really one of the things that we're very interested in, you can see that the same trend applies, and these materials down here tend to be your heat treatable alloys, and these are your work hardening alloys. So with this kind of thought process in mind, we can use this as sort of a bounding condition for a lot of materials. So now let's look at a real coating. Now in this case, I'm looking at an HBOF coating. It's a tungsten carbide coating. It's a brittle material. It's linear to failure. Doesn't have a lot of plasticity. So it fails at a stress level of about 116. This is on a steel substrate, just for reference purposes. But what we're showing here is all fatigue of the coating. So once the coating fails, we're not monitoring propagation. We say, okay, the coating failed, we're plotting the data point. So if you take this single cycle data point and you multiply it by that 0.25 factor, you get something like this. Here's your UTS, there's your design space, and oh, here's your endurance limit, and that's about where it plots. So so it's kind of interesting. A wide variety of materials will plot this way, and you know, and show pretty good results. Now I'm showing this arrow here because if we weren't connected to a substrate, if we were just evaluating the coating itself, we might then have to apply some residual stress factor to shift this curve back and forth. So with that in mind, let's look at actual cold spray material. So this is 6061 freestanding material. These are curves, SN curves of 3 different formulations. We have 3 different elongation values, so 2.5, 3.5, and 4.5. And then, you know, we have a slight difference in UTS. So the upper curve has a slightly higher UTS of 47. So then if we start to do some plots with these materials, we can say, all right, let's take our ultimate strength, and then we'll multiply that by that 0.25 factor. And then if you start to plot these things, you end up, you know, right around here on that curve. So you could see both the so the red is the UTS from, well, the red is from these 2 lower curves, and then the green is from the upper curve. And you can see they plot similarly on this chart. Now, if you want to look at how that might perform on the lot 6061, which is shown right here, you can do something where you then try to shift that by the amount of the residual stress in the coating. Obviously, you have to measure that residual stress, but let's just assume, which is not a bad assumption, that it's in the ballpark of 10 KSI. Well, that would shift out just beyond this curve, and this curve is the endurance limit for wrought material. And now if you want to take a look at 10 to the 5th cycles, you can do the same thing. This would be a constant life plot for 10 to the 5th cycles. Here's your data point, and again, if you shift out, you should expect to see, you know, that your material fails beyond where the substrate would fail anyway. So that's good news. This is how you can kind of use this process for you know, taking some freestanding material and seeing how it might work in practice. So now let's look at crack propagation a bit. So here's an example. I don't have the good data that Chris has, so hopefully he'll be presenting next year on this. But if we look at crack propagation from a carbide material into an aluminum, so this is 7075 substrate, then you can see a significant reduction in the properties, and without getting into the details, this is very close to the threshold performance of the material. So, and this is if you apply shot peening. So, it is very, when you have especially high modulus on low modulus, it's especially the driving force is high. And this is really the last thing I have, and this is aluminum silicon. So this is a lower quality HVOF aluminum silicon material applied to a substrate. In this case, you have a material that's relatively low modulus, relatively poor bonded as compared to cold spray, especially the high pressure cold spray. And what you see is diversion when it hits the interface. And the results are you're getting debits that are similar to the grit blasted alone. So the grit blast gives you a debit from typical, but you're not seeing a significant increase in the debit from this aluminum silicon material. And that's because it's not providing any load support, and it's not then transferring the crack into the substrate. And with that, I don't need to talk to the summary in case there are any questions, and I'm running a little bit late here, so.
No, we actually let you go. I mean, so why don't you just make the last point, because we're gonna go right into our last speaker.
Okay.
Aaron.
All right. So all I'm going to say here is, so when I talked about this curve before, what I didn't say was, and this is one of the things we should really consider as a community, if we've developed a high-strength material like a 7075, for instance, that's significantly better performing than 6061, it's got such a margin above and beyond 6061 that offers a nice repair solution to the lower strength 6061, because even if your material isn't the highest quality, the strength being as high as it is still gives you margin. Whereas with 6061, repairing 6061, I have to make sure that material is sprayed with the highest helium conditions to give me excellent quality, stress, and so forth.
Got it. We just lost you there for a second. I don't know if you're still there, Aaron?
Yeah, I was, but sorry about that. Something happened with my microphone.
That's okay. All right. Well, I appreciate it. And so, like your last statement, low quality repairs may not show a debit, because they're basically not sticking as well. There's not that mechanical mixing that you get with high pressure. But on the same token, they're not going to provide any load support,
Right,
like you said.
right. So if you need the load support, you do need the, the higher density, good quality material, but then you do have to manage your layered structure and so forth to try to divert if they do. So that's it.
All right, we lost